Hi friends, today we are going to learn about CPU scheduling parameters in operating system. Okay, so CPU scheduling is all about deciding which process gets the CPU next from the ready queue and to know how good a scheduling algorithm is. Okay, so basically we look at several important parameters. Okay, so first is CPU utilization. See, this CPU utilization tells us how busy the CPU is. Okay, if the CPU is idle, it's wasted time. Okay, so the goal is to keep the CPU as busy as possible. For example, if the CPU is busy 85% of the time, then CPU utilization is 85%. So ideally, we want it to be 100%. But in real systems it's usually around 40 to 90%. Okay, then throughput. See, we have throughput, so this tells us how many processes are completed in a given time. Okay, so the goal here is to maximize it. For example, see, if 10 processes are completed in 5 seconds, so the throughput is 2 processes per second. Okay, so more throughput means the system is doing more work in less time. Okay. Then third is turnaround time. Okay. Turnaround time. Third is turnaround time. Okay. See, let's talk about turnaround time or TAT. This is the total time a process takes from entering the system to finishing like execution. So we calculate it using the formula turnaround time equals completion time minus arrival time. Okay, for example, if a process arrives at 0 milliseconds and completes at 10 milliseconds, okay, so its turnaround time is 10 milliseconds. So the goal is to minimize average turnaround time so that processes finish faster. Okay, then waiting time. Waiting time. Okay, so this is the time a process spends waiting in the ready queue before getting CPU. Okay, so the formula is waiting time equals turnaround time minus burst time. Okay, for example, like, see, if a process has a burst time of 5 milliseconds and its turnaround time is 10 milliseconds, so the waiting time is 5 milliseconds. Okay, so our goal is to minimize waiting time so processes don't stay stuck waiting too long. Okay, then response time. Okay, response time. So let's understand response time. Basically, response time is the time from when a process enters the system until it gets the CPU for the first time. So the formula is response time equals time of first CPU execution minus arrival time. Okay, for example, like, if a process arrives at 0 millisecond but first gets CPU at 3 milliseconds, so the response time is 3 milliseconds. Okay, the goal is to minimize response time, especially for like interactive systems. Okay, so the system feels quick and responsive. Okay, then fairness. Fairness. Okay, so finally we have fairness. So this means every process gets a fair share of the CPU. So no process should starve or wait forever. Okay, for example, like round robin scheduling gives each process a fixed time slice, ensuring fairness. Okay, so our goal here is to maximize fairness. Okay, see summary table. Summary table. So basically, to summarize, like here is how the parameters work. First is CPU utilization. It's like keep CPU busy, like maximize. Okay. Then throughput, number of processes completed. It's like maximize. Then turnaround time, completion minus arrival, like minimize. Then waiting time, time in ready queue, goal is minimize. Then response time, first execution minus arrival time, goal minimize. Then fairness equals CPU shares to all processes, goal maximize. It's like you can imagine it visually like this: CPU utilization and throughput. We want high, okay, turnaround, waiting, and response time we want low. And fairness should be high so no process stops. Okay, okay. So basically, see, think of the CPU as a worker. If the worker is idle most of the time, your factory isn't efficient. Okay, so CPU utilization tells us how busy our CPU is doing real work. Okay, see, okay, example like mm, if your CPU is busy 85% of the time, okay, so that's good, but the but 100% is perfect. Okay, so why isn't 100% always possible? Because sometimes processes are waiting for IO, or the CPU is idle in between. Okay, so basically high CPU utilization alone isn't enough. Okay, so you also need to balance other parameters like waiting time and response time. Okay, and in throughput, this is like how many processes the CPU can complete per unit time. So imagine it as your system's speedometer for like finishing work. Example, if 10 processes finish in 5 seconds, your throughput is 2 processes second. Okay, so throughput and CPU utilization are related but not identical. Okay, you can have high CPU utilization but low throughput if the CPU is busy doing long task while short task pile up in the queue. Okay, so main goal is throughput's main goal is like maximize throughput without starving smaller processes. Okay, so this is throughput. Okay, so then turn around time. See, basically this is total time a process spends in the system from start to finish. Okay, TAT equal to completion time minus arrival time. Example is like process arrives at 0 ms milliseconds and finishes at 10 milliseconds. So TAT equal to 10 milliseconds. Okay. So low TAT means processes finish quickly, but see, there is a catch. If we only focus on TAT, we might give all CPU to short processes and ignore long ones. Okay, so smart scheduling balance TAT for all processes. Okay, then waiting time, WT, like this is time spent waiting in the ready queue before CPU allocation. Okay, formula is WT equal to turnaround time minus burst time. See, if burst time is 5 milliseconds and TAT is 10 milliseconds, so WT is 5 milliseconds. Okay, so waiting time shows inefficiency. So basically, your CPU could be idle for a long while processes wait, or a long waiting time could indicate unfair scheduling. So reducing waiting time improves responsiveness. Okay, then response time. So uh, so now comes a key one for interactive systems like responsive time. This is how long it takes for a process to get CPU for the first time. Okay, not completion, just the first response. Okay, so in systems where humans interact with the CPU like typing or gaming, so low response time is critical. So a system may have high throughput but feels slow if response time is high. Okay, then fairness, like this is all about giving every process a fair share of CPU. See, imagine a classroom. If one student gets all the attention, then others suffer. Okay, same with CPU. Example like round robin scheduling gives each process a fixed time slice, so this prevents starvation and ensures fairness. Okay, so like fairness often comes at a trade off. So perfect fairness might slightly reduce throughput, but it keeps all processes alive. Okay, so is summary table. Parameter is CPU utilization, and CPU utilization goal is maximize. Keep CPU busy, but don't ignore waiting response. Okay, then throughput. Parameter is throughput, and goal is maximize. So finish more processes but balance small large task. Okay, then turnaround time. Goal is minimize quick completion but balance all process sizes. Okay, then waiting time. Goal is minimize. Okay, reduces inefficiency in ready queue. Okay, then response time. Goal is minimize, critical for like interactive systems. Then fairness. Goal is maximize, like prevent starvation, ensures all processes get CPU. Right? So basically CPU scheduling isn't just formulas. It's about balancing these six parameters intelligently. Okay. So high CPU utilization is good, but if waiting or response time is terrible, then the system feels slow. Okay, throughput, TAT, and fairness, all the all the need smart balancing. Okay, so once you understand this deeply, any CPU scheduling algorithm makes sense. So you can predict how it behaves and why it performs well or poorly. Okay, so that's the smart way to master CPU scheduling parameters. Thank you.